Okay, so we've now got our ideas of sort of unions and intersections and all the rest of it. So now what I'd like to do is go through a few different rules that we're allowed to do for combining different sets. Okay, so we've got this idea of a complement, of a union and an intersection, and just like we have, you know, times and plus and minus, I want to sort of explain some of the rules that we can go about combining different sets. So rules for set operations. Okay, so I'll just very quickly review these. So these are the kinds of things that you're allowed to do, and I'll write it down as a lemma perhaps. So lemma, they'll only prove some parts of it. First, that if A is a subset of B, then if I take the complement of A and the complement of B, then it switches the order of that they're contained within one another. Okay, and that sort of, you can think of that logically, but you could also draw like a nice Venn diagram. So let's imagine we've got a B here, and inside B we've got the set A. Okay, and we look at all the things that are outside A. Okay, so that's this sort of area here. Oop, I'll draw that a little bit better, like this area here. That's sort of A complement. Yeah. And so all the green area here, notice it contains all the stuff that's outside B as well. Okay, so that's the reason for this relationship here. All right. Okay. So you can see that a lot of these kind of set operations you can view in terms of drawing an appropriate Venn diagram for your problem. Okay, so just looking at the kind of bubbles for each set, and then looking at how they kind of intersect with each other. Okay, so here are a few more. One thing to say, which I think I mentioned before, is that unions and intersections both have this property that it sort of doesn't matter. So normally if we had brackets, that would mean I'd have to do this B union C and then union with A. Okay, and the point is that that's the same as A union B and then we union with C. Okay, so in other words, it doesn't really matter how we go about combining unions together. There isn't any fixed way that we need to go about doing unions. So that's sometimes called like associativity property, and it's the same for intersections as well. Okay. So if I do B intersection C and then I intersect with A, that's going to give me exactly the same thing. If I do B intersect A with intersection with B and then I intersect with C. Okay. Okay. Another property that we have is sometimes we want to take an intersection of, say, B union C. Okay. And now the way to think about this is a bit the way that you would multiply out some brackets. So if I had kind of A times B plus C, then that's the same as A times B plus A times C. Yeah? And so that's the same with intersection and union here. Okay, so this is going to be the same. I could sort of expand it out in the same way I would normally with multiplication and addition. Oops, silly me. That's be a union and then A intersection C. Okay. The interesting thing is that this also works the other way. So notice that A plus B added to B times C is not equal to A plus B times A plus C. Okay, That's not true, but for sets it sort of is, which is interesting. If I take A union B, okay, and then B intersection C, okay, then that's also equal to B A union B intersection A union C, okay? So it works both ways. We expand out in the same way, whether it's union or intersection here, all right? These are also sometimes called De Morgan's laws. Okay. Another thing to add, again, want to do with complements. So if we look at A union B and look at its complement, then what this does is essentially apply a complement to the A, apply a complement to the B. And we could sort of think of it like union complement is equal to intersection. Okay, so we sort of apply the complement to each part like you would a power almost. At least that's how I think of it. A complement intersection B complement. Okay, all right, so if you look at sort of, yeah, well, if you're not in A or B, then you must not be in A and you must not be in B. It sort of makes sense when you say it as well, all right? Similarly, if we look at A and B, it's sort of, the complement has the same effect of switching the intersection around to a union, okay? So A complement union B, okay? So if you're not in A and you're not in B, you must not be in A, or you must not be in C, in B, sorry. Okay? And how would you go about proving all of these results in this lemma? Essentially, the way to go about doing, which I think is a perfectly reasonable, rigorous way of doing it, is to draw a Venn diagram in each case. So here I'll just do the kind of De Morgan's law for this one here. So proof, and I'll just do it for sort of the first part of part 3, is we could draw a Venn diagram. So I want to show that A intersection B union C is equal to A intersection B union A intersection C, okay? So if I just draw my sets, A, B, and C, okay? And I want to look at A intersection B union C. Well, B union C is all this area here, and the part of the union of A and B that intersects with A is clearly this area here. Okay. Now, I want to look at how that compares with A and B. Okay. A and B, notice, is this area here, and I union that with A and C, okay, which is then this area here, okay. So if I combine A and B, and I combine that with A and C, and I'm just going to end up with the same thing as A and B or C. Okay? Alright? So we could do that for each of the cases up here. Alright, and we'd end up with the correct set operations for each case. Okay?